Okay, so before we get into example 3, we need to talk about this very important concept. Now, if you have your note packet, it's down at the bottom of page 7. I just moved it up to this area so we could all see it here. So there's this idea about exponential. We have two ways we look at things. Either we are growing or we are decaying. So we say exponential growth or decay. Now, our exponential model, here is it in general. The amount you have is equal to the starting amount that you have times your growth factor that gets repeated some number of times. So your amount that you have is what you start with times your growth factor repeated, however many times you decide. So this was our model. It was y equals a times b to the x. And what I want you guys to look at now is that when we start modeling, we need to have a kind of a slightly different formula that more accurately reflects the things that we're doing. And what I mean by that is this, is you will see this generally. A of t equals a times 1 plus r to the t. Now, as you can see, we're just kind of using a different representation. Instead of y, we're using like f of x. In this case, we're using a of t. A is the same. We now change b to this idea of 1 plus r, and we're changing x to this idea of t. So this t more accurately represents time. So in most situations, we're talking about how things change over time. This is still our growth factor. And then certainly we still have our starting amount here. This is our starting amount. Now, the only difference is when we talk about decay, the only difference is that this a of t is equal to a times 1 minus r to the t power. So we'll see how this works, but I just want you guys to be aware of this, is that we're instead of doing a times b to the x, we're going to do a times quantity 1 plus r to the t power. Because a lot of times when we model, we talk about how things are growing at a certain rate over a certain amount of time. So this is our growth over here. And then the only difference in our decay is that we are subtracting. And the last thing I want to say is that r, which equals our rate of growth or decay, always needs to be a decimal. So most of the time, you guys are going to get it as a percentage, but it always, always, always needs to be in a decimal. So if your growth rate is 5%, then you would use 0.05. If you're decaying at a rate of 2.4%, you need to use 0.024. And if you're growing rapidly at a rate of 35%, you need to use 0.35. Okay, so those are just a couple things that we need to make sure that we talk about before going into problem 3. So problem 3 it's pretty straightforward if you can comfortably use this concept here. All right, so the population of a large city was about 4.6 million. Right away, this is our starting. So here, I'll put this down here. Example 3, we are going to model with exponential. All right, so the starting value was 4.6. 4.6 million, okay, in the year 2010, and it grew at a rate of 1.3%. So our growth rate is 1.3%, which we know we need to use 0.013. And it also said that our population, it is at growing. So we know we're going to use our growth rate function, which is a times 1 plus r, because we're growing here. And then naturally it says what exponential function models the population over a 4-year period. So sure enough, 4 years, our t value is 4. Okay, so we're going to use this idea. So here's our growth model. So we want to do it after 4 years. Our starting is 4.6 million. Let's just use 4.6. It's growing at 1 plus our rate, which is 0.013 for 4 years. And we'll clean it up by just doing 4.6 times 1 plus 0.1013 is just 1.013 to the 4th power. So again, as we can see, since this value is greater than 1, it means that we're going to be growing. Okay, so as we can see over here, 4.6 times 1.013 to the, in this case, 4th power. Okay, so this is part A here. So now part B is asking us, well, if the population continues to grow at the same rate, what will the population be in 2040? So let's get down all the things we know. Our starting value was still 4.6 million. Our rate is growing at the same rate of 1.3%. So that's going to be 0.013. And now T is our number of years since starting. So since the population we're asked about in 2040, remember, our population, the starting was in year 2010. So how many years, always think of T as how many times over it's been repeated. So in this case, from 2010 to 2040, we've done it for 30 years. Okay, so we know that we're going to use growth because it said that we were growing. So let's go and do it. So we know that our growth function is a times 1 plus r to the t. We are trying to evaluate after 30 years, so we want 4.6 times 1 plus 0.013 to the 30th. And this is where I would go to the calculator. I would type this in just like it is. 4.6 parentheses 1 plus 0.013 raised to the 30th. So we get 6.777. And in this case, we just want to make sure that we know that this is in millions, because certainly we started with our population in millions. So let's call it 6.78 million people. So certainly over 30 years, if you're growing consistently at 1.3%, it's going to skyrocket. It's going to grow exponentially. So make sure that we always put our rate as a decimal. You always want to think about, am I growing or decaying based on whether my number is bigger than 1, therefore it's growing, or smaller than 1, therefore it's decaying. And then you always want to just say, what's my A value? What's my rate? What's my T value in time? Plug it in. Good to go.